Okay, so good morning, everyone, and welcome to MFPS number 40. So it is the fourth year of the conference, and that is kind of, as Alex was reminding me, that means XL, extra large. But we are not exactly extra large. We are collocating with ACT, as most of you know, and that makes for an interesting kind of conference with lots of possible interactions. I have not much to say. I just kind of wanted to remind you that that MFPS is a conference that's very dear to us, and it's nice to see some people that have been around for a long time, and we have Alex and I think that we have a very exciting program for you guys. Our invited speakers are brilliant, kind of starting with Philippa, and we have this very special session for Phil Scott, which is, it is sad, but it is good that we are celebrating his work and everything. So without further ado, Alex is your chair. And of course, I forgot to say, but Sam is not here, so you can tell him later. We're also very thankful to the local organizers for kind of all the work that's involved in doing MFPS in Oxford. And it's good to be back in Oxford. So without further ado, Alex is the chair for Philippa, and we can start.
Okay, well, thank you very much, Valeria. And it's really a pleasure to have Philippa Gardner as our opening invited speaker for MFPS XL, extra large, as Valeria said. So if you don't know her, Philippa is Professor of Computing at Imperial College, where she leads the Verified Software Group.
It changes the name. Yes,
right. And one of the really nice things from an MFPS perspective is that Philippa is both applying and also developing theoretically reasoning about formal reasoning about programs using technology such as separation logic, which I think is one of the great contributions that has essentially come out of the crucible of MFPS-like thought over the last 40 years that we've had MFPS conferences. So I think Philippa very much is doing work very in line with MFPS, and it's also, from a personal point of view, a pleasure to introduce Philippa this morning, since we go back a long way. We both studied at this august institution together a few years ago. So anyway,
and then we're sweating.
And then yes, no, indeed. I mean, we can read the whole story. But indeed. So anyway, Philippa is going to tell us about compositional symbolic execution. And thank you.
So Alex and I were PhD students together, or near enough together, and I was pretty terrified of him now. So I'm extremely, still terrified of him now. He's chair of the board. That's pretty much, yeah. I love the fact that Valeria said how dear MFPS is to us. And Alex mentioned the legacy of MFPS being sort of quite a pivotal point of separation logic. There is Peter Hearn, Victor Bacheridis, John Reynolds, me, others who I've forgotten, Steve Brooks, who else? Many I've probably forgotten, but absolutely it was the place to have the conversations and the discussion. So actually it was extremely important. And the other thing to say, I'm having a very weird deja vu moment, because last week I was in this lecture theatre giving a talk at the Oxford CS annual conference, and there was a women in computing talk that I gave. So this is a different talk, but it's quite weird. So I'm using this beginning just to put up a few, some favourite lovely photos. Of course, it all started with Alan Turing, but went on to Tony Hall and Robin Milner, talking about verified software. And these are some papers And the point is, at the time of being PhD students, we were reading these papers and we were sort of in our fledgling start of verified software. And now what's happening? Well, proof assistants are mature. They weren't when I was a PhD student. Verification tools are tractable, and real-world programs are being formally specified and verified in academia and industry. And we don't even think about it now. But it wasn't happening when I was a PhD student. So this shows over that generation what is possible to do. So given where we are now, what's possible for that next generation? Good luck, guys. Yeah. But aim big, because you don't quite realize quite what's happening, actually. The good stuff will fly. And my particular challenge is that I like to work on foundational mathematical techniques and well-engineered tools to reason about open modern software at scale. And some in the audience might have a bit of a snigger at this, given that they know the old Philippa. And actually, sort of really, I'm a theorist, yeah? And I don't spend my time coding. That's not what I do. But I got a real gift from going to Imperial, which is the students, especially the students that I came across, were really good mixture of theory and practice. And so if I were to thrive in that environment, I had to adapt. And I found a way of adapting and joining different types of people together. And I like doing it. So that's why I've ended up where I have. And to say at scale, that's really, in part, it's a little bit taking the piece about with my wonderful colleagues who went into industry and took their theoretical work and made it fly in industry and go, way, we've done this at scale in so many ways. So I'm putting in my version of at scale too, because you get the small maths right, the rest comes, but they know that for what it is. So. And there's been a huge number of people working on specification and verification of language standards, libraries, and ad hoc programs. And that's really what I'm doing. And today, I'm going to talk about compositional verification and true bug finding. But I've done a lot of work on language standards, and in particular, where it's flying is with the WebAssembly work, because you've got the formal semantics, so mechanization can hit as the language is evolving. And Conrad Watt and I have got a big project now doing a lot of that. Started from Conrad, who knew what I was doing on JavaScript, so that's how we intertwine. If anyone's interested, talk to me afterwards, but we've got a PLDI paper next week. I've done work on concurrency, not talking about that today. Here I'm at compositional verification and true bug finding in the sequential case. I just wanted to put this up. This is from a paper from the White House. And I think people do know it. It's beginning to get around. And in particular here, we've got memory-safe programming languages, memory-safe hardware, formal methods. Now, I was director of a research institute funded by GCHQ for about 8 years. And one of my jobs was to get one sentence into the papers that GCHQ were writing that had the word formal methods in. So to go from that one sentence to this, for me, that was very personal. I went to a real result, even though I probably hardly did anything about it. You know, there's many people that have contributed to this. But actually, this really is a call to arms for all of us, not just the cybersecurity technical people, which is what the paper is talking about. Because what they're saying is programming languages are the foundation. that means formal semantics and mechanized semantics and language standards done well is at the start. And then what sorts of languages? So they're not talking about ML, they're talking about Rust, but WebAssembly is memory safe language too. So it's a little bit on the way. And I think that's something to highlight. And in particular, I realized, this guy here, Andreas Rosberg, he took the ML module-like work of Robin, and that's what the encapsulation is. And so it's that sort of, and he's got those sorts of results that Robin had. And because of the mechanization, things like, of course, type safety, but also modular instantiation correctness can be done with this language. But I'm going to talk about compositional verification and true documentation. So I've got the auto bit up. So what I'm going to talk about is going to be based on separation logic. And the germs of that work came from Bob Bursell. And if you look at this original paper, it's very formal, just writing down his thoughts. But they're really good thoughts and are absolutely to the point of what that separation logic work turned into. Somebody who's not mentioned enough is David Pym, who with Pete O'Hearn did logical bunch implications that led to the separation logic work. And he had a lot of inspiration on that. The separation logic guys are Pete O'Hearn and John Wales, as I think we know. And in particular, Pete O'Hearn had this journey of going, well, the journey starts here with the category theory, through to the logic, through to the startup company, and then into what's now Meta, where he's got his infant. This work here is about overall approximating reasoning, and really it's about verification, and then they used it for bug finding in the info tool. And there was actually a bit of a mismatch going on with what they were doing in practice and what they were doing and what they'd previously done in separation logic. And that's got sorted out with new stuff coming along, which is something called incorrectness logic that deals with true bugs, meaning that it's an under-approximating analysis where if you find a bug, it's a real bug, theoretically. It doesn't mean it's a useful bug, but theoretically it's there. And that's led to Meta's Pulse, started out by this guy, Jules Villard, and who is still at Meta, and gone now. He's at Lacework. And they, Raj, my colleagues, come along, and these two guys are working a lot on the incorrectness. Missed something. And here, there were a lot of tools based on separation logic ideas, in particular, over-approximating analysis, working with verification. And they're Verifast, Viper, something called CN that's just started at Cambridge with Pete Saul. Verifast is Bart Jacobs, and Viper is Peter Muller. And my group has a tool called Gillian. And all of these tools are based on the same technique, which is compositional symbolic execution. And there's been formalism associated with these tools, but this formalism is too connected to the tools. And it's not, the formalism hasn't been pulled out to be independent of the tools. And so this is what I'm going to talk to you about today, a definition of what compositional symbolic execution is, so that implementations in tools satisfy that. And in particular, so it's a technique that is based on partial state, just as with separation logic. Can we turn this off? Is there any way of, this is echoing really badly. That's why I keep on going over there. But then I'm realizing I'm going backwards and forwards. I don't think so. No, it wasn't.
Oh, no, but on Zoom.
Hello? Yeah, no.
Have you joined on the?
Where's my supervisors?
Does anyone know how? Oh, yes, you're in that meeting to meet.
Hello? Here.
Okay, can you share it? No, don't leave meeting.
Not leaving.
Okay. Yeah, share it. Okay.
Excuse me, sorry about that. I was going to drive me mad throughout the whole talk. So basically, I'm going to talk about this technique that's a technique for semi-automatic verification and automatic true bug finding inside a tool. And then I'm going to describe an extension of Gillian that gives the first tool that does pin them both together. And the separation logic, we know, has this idea of one works with partial state, not the whole state. We work with the state that we need in order for the job to be done, rather than thinking about the whole state. In concrete operational semantics, work with whole state. I'll explain more on that later. So we have this idea of symbolic execution, and it's manipulated by so-called consumer and producer functions that I'll explain. It has I'm going here. It's easier to explain. We have the idea of partial state. It's symbolic. What that means is, instead of working with a concrete state with address n points to value 3, we have symbolic state. So address 5 points to 3. We have symbolic state with symbolic variables that are a bit name-like, that are giving a more general account of what the input might be. And then we've got, just like one would have in normal operational semantics, one has a path of this, of how this symbolic state evolves as one goes through the command. And in particular, when we get to a branch, such as an if statement, we've got the choice to go true, false, or error. And so at this point, we add a first order formula to say this Boolean has to be true, this Boolean has to be false, or we have the error case that the Boolean doesn't hold. It isn't Boolean. So basically, we have this symbolic state. We have the idea of this path condition that explains how you're walking through the program, and in general, and you have the tree of possibilities. And then you have an outcome, which is also a symbolic state that can either be giving a result that is a real result, or it can be error, meaning that you have some form of language error, such as a memory overrun or use after free or something like this. Or you have something new, which is missing error, because we're in the separation logic thought process, that means that we're working with partial state. Because we're working with partial state, we might not have the resource we need in order for this C to find. In particular, if you're doing an update of a particular cell, you might not have the cell. The symbolic state might start at empty. So we have the missing case for what do we do when we don't have the right state for us. Just to lock in the people who know about a little bit about this sort of thing, the bioabduction work of Pete O'Hearn, you get fixes from errors, these missing errors. So we've done it theoretically, he was having the idea of that. And with over-approximating reasoning, in this symbolic execution, it's possible to drop information along the execution paths, meaning you can get more abstract. Instead of knowing about a symbolic variable having value 3, we know it's greater than 0, something like that. We have abstractions possible, but we can't drop execution paths. And you know this from something like separation logic, because provided you terminate, then you have to land in one of these. But because you can drop information along the execution paths, it means that you can say that something is a bug when actually it isn't. It's not a true bug, it's a possibility of a bug. And so in the under-approximating world, that's much more known to the tool developers working on symbolic execution, they are very much wanting to be true to that bug finding. And it is possible to drop execution paths, but it's not possible to lose information along those execution paths. So be very careful of what you can do along. And what happens with incorrectness separation logic, it has the condition also that anything here in this set has to be able to come from here. You have to, given anything here, there's something here such that you have a path to it. Which means that the bug is true because the bug is reachable. Now, what's going on here is what sort of people have known about. We can explain it a little bit better now, I think, because of the incorrectness separation logic work. But basically, we've known about this. The tool developers know about this, and the problems with it are that you can't write function summaries. And you can't write function summaries in the old traditional style of working with first order logic summaries because of the lack of this partiality of the state. So for example, in something like CBMC, that's a very famous tool based on symbolic execution developed in Oxford here. They can do function summaries with respect to the variable store, because the variable store, you can work globally with the store. And the reason you can do that is because the functions are very good about keeping track of how the variables are working. You go to a separate place to work with the variables, then you go back to the store you were originally at to continue with what's going on. So from the point of view of the variable store, you're okay to work with first order logic and be global. From the point of working with the heap and recording properties of the heap, we haven't got that same connection, the same care going on between what's going on with the main bit of code and what's going on with the functions. The heap's just getting changed, and you can't first order logic is not enough. You need the separation. And this is actually the magic of separation logic in sequential programs, for sequential programs. There's a whole wad of work to do with concurrency that needs separation logic for other reasons. But for the sequential stuff, it's all about how does one do the function. So when I say compositional symbolic execution, what I mean is that we can add functions to what's going on. So in particular, one can do function calls and one can work with function sets. So what I'm going to do is try to give you an idea of this world that's to do with symbolic execution. Don't worry, I've got the slides that are more detailed. I'm just giving you an overview. This world that is symbolic execution and this world that is separation logic. This world of separation logic is totally independent of any tool, is not, it is written in a language with a semantic satisfaction relation that can be used, never mind what tool it's come from. Whereas here, I'm talking about a particular operational semantics for this symbolic execution. So the sort of summaries we work with look like this. And basically, it's a bit funny notation, but it's just mainly what you know. So this is really a Hall triple, a separation logic triple, but we've separated out what's happening in the OK place and what's happening in the error place. That needn't be done. It's done because of motivated from this side. It's not completely necessary. And this side is incorrectness separation logic. So this one is the normal one. Whenever you have something satisfying this assertion, either things don't terminate or they terminate and you're in this world. This world is everything here has to have something here that goes back to. And here we have a symbolic state. And I've just separated out the symbol. I use hats to remind us that we're symbolic. And we can, that's all. And we can split state via composition into two parts, so splitting and joining. And that's the normal separation logic land. And in particular, I'm writing this notation to mean this bit of the symbolic state here matches with this P, this assertion. So we can do that match between this P and this symbolic state, sigma P. And we can consume the precondition. And what that means is that we can take this bit off because it matches here. And we're left with the frame that's framed in that symbolic, in that separation logic land, but translated to this. So here we have the frame. And now we can produce the post condition. This is what's going on in the tool. There's functions consume and produce. And this is in every tool that uses it based on separation logic, well, at least the ones I've written up there. And the produce takes whatever, let's say the Q OK, and puts the relevant bit in there. And whether we be in the OX land or the UX land, one gets a soundness result between this. We want that soundness result between these two. So basically we have two functions, consume and produce. The consume function depends on which mode you're in, and I'll say why as we go. It depends on the assertion P, a beginning
substitution that says what this x is. This x is it's the call of this function. And we have the state that we've got. And this is going to get to a bigger substitution. This is bigger than this, and that's to do with how this matching happens. And we get left with the frame. And then the produce function takes the assertion queue, takes the substitutions that you found out and the frame, and gives back the state you wish. And the join between this side and this side with these functions is given by what we've done, which is this axiomatic interface. And this axiomatic interface is basically saying what these consume and produce functions need to satisfy, what properties they need to satisfy. And I'm not expecting you to see all of it. So these are the properties. And it looks so small and pretty.
Yeah.
It was horrible. It was so long. It's so little now. But so after a huge amount of sorry?
You reduced your font size.
If only you'd seen. Yes. So basically, we've got well, formalist properties associated. I mean, it's hard stuff. That's what. I'll try to indicate this later. We've got the well formalist properties of the memory. We've got something that is very normal with symbolic execution, which is you've got this path condition. You're going through the path. For example, that if you're splitting off branches, a while would do the same thing, etc. Basically, you're building up extra conjunctions of first order formulae about variables. And so, of course, it is the case that the pi at the end, this pi prime, implies the pi at the beginning. That's a well-known property. And then there's a covering to make sure that you've got enough substitutions going on for the consumer. And soundness completeness properties for OX and UX. And these actually have got better. We've got soundness completeness in as one now, whereas they were separate when we published. But the point about this is something, I think there's something really interesting about this. That interface is independent of the memory model. It's independent of the language. And it's independent of the implementation. So this means it doesn't matter what memory models you're putting in, it doesn't matter what language you're using, what tools you're working on. Actually, these are the properties. Which presumably can be written beautifully, but I haven't got the brain to do it. So those category theorists interested, help. Next, been chatting to us a bit. And the point is the function call rule is sound, assuming the properties of the axiomatic. So we have that. But in particular, this is only part of the story. And I'm saying that I think this work is very beautiful, and I'm saying it at this level of compositional symbolic execution. But it didn't come from here at all. It actually came from the practitioners. It came from the tool we were working on down in with this Gillian tool, Gillian, where it was so full of optimization, so full of stuff. It was really difficult to grab at the ideas that have come percolating out to this place. And one key way that we were able to do with this was this guy, Andreas, who formed the bridge between the what was going on inside that Gillian platform and what we needed to do to get to here. And these guys here, done in order of, you know, as with normal academic projects, people leave, people come. So it's these guys first, onto here. And so the beauty of this Haskell implementation was that suddenly we could all talk to each other and we were all able to work. So he was the interface between what was happening in the grungy code and the beautiful code. And then from here to here, Daniele, who's there, insisted on not just the Haskell code, but actually the code, the pseudo code where she could prove her theorem. And it wasn't just her, but she was a driving force for that, so that we actually got the results here based on the pseudo code that has a dead link to this Haskell that's as close as we can to what's going on with the Gillian platform. At some places we had to change, and the Gillian platform will evolve to those changes when it can. So in particular, I've told you about the consume and produce functions, and now we need to, so I need to give you a hint of what the implementation of these consume and produce functions are that satisfy these axiomatic properties. Because otherwise I've told you half the story. I've given you the interface and what it means to use the function call rule. We can. But now, what does it mean that actually what the tool is doing satisfies those? So this is consume. And here we have, I've just opened up the symbolic state slightly. So we've got a symbolic variable store, symbolic heap, and symbolic package. And we have a logical assertion that I've split into two parts. The first order part that corresponds to that high, and no, it doesn't, sorry. That first order part and the part that describes some of the heap. And here we have function specifications looking like this. And in particular, let me, something I might have emphasized earlier and didn't. These function specifications, for example, might only update one cell in the heap. So because of that, they really are just working on this tiny littlest bit of heap necessary for that function to fire. There needn't be such a draconian statement of the most minimal thing, but it's just on a sum of the resource, not on all of it. That's why partiality is so important. So in particular, I'm showing here a little bit of a limitation of our work. We are working with expressions looking like this. There's a whole host of results about matching, saying what sort of expressions we can work with. We're at the start of what's. And this is the normal separation logic assertions using some predicates such as lists and some cells assertions. And the question is there a substitution and two heaps such that in the OX case, we have the validity statement that this pi implies that there's a connection between here and this this HP. There's connection between here, that this bit is true, and that this bit is the HP bit and the rest. And this is a validity statement. In the UX world, it's a satisfiability statement that pi and this other stuff is satisfiable. So there's slightly different things going on between the two. And one has to be careful about that because it's exactly corresponding to whether one's thinking with an over approximating spec or an under. This is matching to find the substitution. We have frame inference, and let's see it at work. So here is this, here's an assertion. We're asking for this function call. We're wanting this function consume, this consume function here. And we start with the putting, where is it? This x equaling, it says b, it's that e, I haven't changed it, I should have changed it. And basically, given these functions here, these functions is saying to us, because of this parameter x, that we have the knowledge x. We have this knowledge x, and we know this precondition p. And so because of this, we can learn, create what we're calling a matching plan, which allows us to write this p in such a way that the matching is easier. Starting from this x, it's about following spaghetti-like through this assertion to get automatic reordering of assertions. And this is something not done by Verifast and Viper. It is done by Gillian, and all of this is inspired by Gillian. And the point is, so here we are, we start at x. So here, given this x here, we know what the y is. And we don't know what the y is in terms of we haven't linked it to a particular symbolic state. But we know we're going to find some value for it. We just don't know what it is. And then if we go on, we've got this z that, given that we know y, we know z. So here it's giving that information. And then when we've got z, we know what's happening with w. We don't quite know it. We know we've got a placeholder for when we know it. And then we, with this w, find the v's, and the v's is all something which we don't know. So this matching plan, we can do connected to these function summaries when we have the function summaries, not when we're calling the function. Yeah, so this is something that we can do at our leisure. And now we do the consume. And for the consume, I'm not going to go through this. It's about finding these O's and going through the spaghetti of what's going on. So here's particular H. I'm not going to go through this, it's too much, but just to say at some point one had to unfold the list function to get what we wanted. So you can see that this sort of matching is going on. And these big O's are getting found. And we end up with what we need to, with this new state, producing the result. I'm going to drill down once more. We've got this, you're not going to see this, I understand. You've got this, oh, that's too scary. We've got this consume function, and its mode depends on whether it's OX or UX. And actually, even though, and we've got a theorem that says roughly what I've just shown you satisfies the axiomatic interface, meaning that this algorithm for consume and produce works. But this is a bit expected. The actual place where the modes are in the success rules, there's more story for the error rules, but here are the success rules, is all to do with those pure volume. And it's understanding how validity and satisfaction are working for these pure first order formulae. That's it. So as a particular example of that, let's assume you have the state where we know that Z is between 500 and 1,500. And we have the starting assertion that Z is less than 1,000. Is it the case that from this pi, Z is less than 1,000? Of course not. But is it satisfiable? Yes, it is. So these are the differences between what's going on with OX and UX. And sort of almost more importantly, this is the only difference between what's going on with OX and UX. It's gone to that very simple place. There's lots of lots of limitations. Because I'm short of time, I am not going through them very much. We are at an improved place compared with other tools. We think we can do better. We are in a unified place because we just spotted what we needed to do to tweak the tool, and then we tweaked the tool. So that's why we got it, and we're hoping that Very Fast and Viper would have the same tweaks. We don't know. Haven't done the chat with us. So, but the cons is that the equational reasoning is very limited, but we've got a master of matching and who's doing ongoing work and is feeling that pretty confident. She said, call it ongoing. And I was saying, can I do just done? And she went, no, say ongoing. So that's where it's at. Yeah, it's fair enough. That's why it's there. So that is where we're at. And just so what I haven't talked about is this Gillian platform that was absolutely the inspiration to start this. And so far, what we've done at the moment is work with just a simple memory model. But the whole point of the Gillian framework is that it's parametric with respect to all to the memory model. And so, for example, because of that, we've got instantiations that are very different from each other, because we can put in whatever memory model we like. And we've done JavaScript, C, and Rust. So we've not caught up yet. We haven't done the parametric case at the compositional symbolic execution level. Well, actually we have, in the sense that we've got now, we're doing it now, but we haven't published it. Yes, I can do it. So with Gillian, we've got a core symbolic execution engine that isn't actually overall under what we're calling exact. And basically, we haven't made the choice at this point. We can put in an arbitrary memory model, and we can do a whole program symbolic testing like the CVM CV. In order to work in this compositional place, at this point, when calling that function, one has to say whether one's in an OX or UX way. You can't stay in the exact place. And in order to do this, we're not only plugging in the memory model, but we're also having to work with assertions. And we're having to put in so-called core predicates. In separation logic, it's things like cell assertions. Cell assertion is a core predicate. List assertion, a list predicate is not a core predicate. It's the smallest little thing. And with this, we can do full compositional verification in the style of Very Fast and Viper. And in particular, for that, we have to have that OX switch. And then if we take the UX switch, then the application that's having the most popularity at the moment is the true bug finding work. And with our fixes from error approach and this UX switch, we have automatic composition of true bug finding in the style of InfoPulse. Not in the style of InfoPulse because they're industry and there'll be a huge amount that they've done that we're nowhere near. This is an academic tool for describing the work we've done. But even though I say that, the characters in my group, some of them are so interested in that real world language and that real world analysis. So what I love about the group is that one has all sorts. And so we've ended up with instantiations that are actually real world. So we have a Gillian Weil for teaching and experimentation, but we do have these really quite macho instantiations, with this one not published, but really on the way. Sasha's just submitted his thesis. So it's very on the way. And there's been real applications done. So the one I'm particularly proud of is verification of some AWS code. It's quite important AWS code, and we've only done a little bit. And what happened was that a developer inside AWS just routinely puts in first order logic for me to as runtime checks through his code. And he's got some JavaScript and some C. So we took those first order assertions, and then we did our verification work on that code for JavaScript and C, working with our separation logic and then abstracting to his first order place. So, and there's actually rather a nice story there that took a long time to do, and came from the developer and came from specifications outside of the our world. I think this Gillian Rust work is going to be extremely interesting, because suddenly the specifications are to do with Rust types. So we've got specifications on hand that we can easily work with. This is a student now in my separation logic course. I've been doing it now over 5 years, and we've got Gillian to the stage where we can actually have a lab on it. That took a while, and we've done it for 2 years, and they love it. It's actually inspirational, and the guys that are doing it are Sasha, Petter, and Nat, and there's Daniele, who's just come to Imperial, I think in 22. And this was, Daniele was learning Gillian as her first introduction to what she ended up contributing to. So basically, the reason why we were able to do it is because of this guy, Nat's debugger. And before that, we didn't have the right interface. And so before, we were working with the grungy logs. And in particular, Sasha and Petter did that AWS code on grungy logs. So the idea that they found, the persistence needed to do that was huge. But now we're in that better place. I'm not going to show you. Basically, you can see that that it's looking pretty nice in terms of an interface. The students can now use it. If anyone wants to see it, I'll show you what. And there's a little bit of a debugging story. Basically, this guy Nat is a real engineer. And he's taken DAP and done symbolic DAP, and he believes he can use it for many tools. He's experimented with Gillian. The next one is doing Jules, which is his second supervisor or outside supervisor, and he's going to do Interpulse. And the thing is to see how much this debugger can be used. It seems orthogonal to the tools that we're using. That's a high-level version of what it is. So I basically told you this story. Here to here is now pretty satisfactory. And in particular, I'll go. In particular, here, before, the work I've told you wasn't parametric. We are now parametric. We are parametric in 2 ways. We're parametric because of this COP formalization verification, but we're also parametric because of Sasha here, who has just completed his thesis. And you can see I've got the biggest smile on my face because we've got opinions in the group. So we have two parametric compositional symbolic execution, and eventually they'll merge into one. And in particular, this is there was really good reasons why there were two. And in particular, the Gillian platform is Sasha came along. He threw out the core, or inspired by the core, he put in the monad approach and his thesis on monads, because of course. And then, also because he's an in-depth functional programmer, he's working on state models and state transformers, and building up these models in such a way that just by construction things are well formed rather than a little bit messy than they are now. So any minute now, that Sasha work is, it's been submitted. Where it's going, we're in next generation. We're trying to link up the two ideas because these guys, they've cleaned up a lot and they've made other choices that have cleaned up. So how do we get it together? We don't quite know. But we've gone away from Haskell to comp formalization, partly because of the characters involved, but partly because it's obviously a sensible choice to do. We now have a new PhD student, Simon Cobb. And there's going to be a new generation, Gillian. Gillian is the only tool, I believe, that is parametric with respect to the memory model. We now want to be parametric with respect to the memory model and language, because the only thing we need for those function call rule is the properties. So we can get much more parametric here and be a much wider plan. So in another talk, when I was taking the Mickey a bit, so I'll take a Mickey again. In another talk, I first had a field of two wild horses going off in all directions, and then here we are now with a little bit of the theory and practice coming together. But of course, there's much more to do, and anyone in the audience having ways of helping us on the journey. We're not those category theorists. We would love to be, but never were. And never mind, I came from Edinburgh, so as much help as possible, please. And we have a compositional symbolic execution, Gillian, past and current team, and it's these guys. Thank you.
Thank you very much. Yes, thank you. So I have a question about symbolic execution. In areas where the SMT solver might struggle a bit, like when you have reasoning modular algebra theories that are not theories in the SMT solver, could you do something with that if you have a specific application that's an algebraic class that you're computing with?
Okay, from the point of view of this work,
yep.
I have nothing to say about that because I am on the ideal SATSL. Yeah.
Okay.
Yeah. So and then what does one do with a SAT solver that's not ideal, etc. So I can only go with the answers coming out right. So I'm assuming that the answer's right. But I'm also assuming that one can't get the answer and one that, there might be a problem. So one way of doing it is in the UX way, there's not a problem because you can always cut paths. In the OX way, I'm always wanting to be able to say a stop, to say actually abort, things. So think that outcome logic stuff, right? So that's how that just at some point you have to add more to those
outcomes. At the moment, I've got okay, error missing. And it's allowed that you just stop because this chunk you haven't verified yet, but you might be able to.
So, I mean, if you think about the chunk of trying to farm through the tool, right? How much would you gain by trying to improve the you get fewer timeouts, obviously, it's over.
I have no idea. I know nothing about SPP solving.
Philippa, you said that properties 1 to 7, these are they were independent of the memory model and implementation. Do I understand that right? It means that they hold across all the implementations and use them.
Yeah.
Each one.
So-
and parametrically, you have separately extra properties that talk about the memory model and implementation. Parameterized.
Yes. So from the point of view of CSC, what I've said here, we're on one memory thingy. From the point of view of TSC2, what's coming up, we are parametric with respect to that. So absolutely, we pull that out. And then from the whole point on what I've said here is you've got that interface where you've separated away from what's happening with the client code and what's happening at the implementation. Just like what we were doing with the components, you know, that cat article that time ago, that was that two-sided interface with the clients and the implementation. So it's happening just as the frame, you know, separation logic and frame is important precisely because of the functions. So that's where, you know, that two-sidedness is the
So the UX, a bit like different kind of mode insertion. Is there ever any need to kind of mix the two together? Yes.
yeah, I don't have a good answer to that. There's very subtle
I mean,
answers.
you're probably more pressing problem.
Yeah, and in particular, we get this, you know, sometimes people say this to us because, you know, there's that Patrick Scoffwell work on the main must stuff and alternating between.
Yeah.
And so we do need to think about this. And I don't know fully the answer at the moment because it's really about, you know, that satisfiability and the validity and where can one and where can't one. So I can say it sort of superficially, which is you can I'm not going to even try to say it. I'm hesitating about it. So in Peter O'Hearn's incorrectness separation logic work, he's got some way of saying from one you can get to the other. But I'm really hesitant about thinking that that's the whole story. So there's a bit in that literature, and I will say it inaccurately. That's why.
Yes.
Can I just compliment your answer?
Yeah.
So the place where you have to do the subjects is when you are doing consume execution of consume function. So we do need to worry about operational things. That's why when she was showing the matching, she said our language is very simple. It's because solving the matching problem is complicated when you mix operational theories. So, but it's fine. I mean, the work I've been doing, and I don't want to play that it's solved. It's fine if you work with, for instance, video groups, and then you work with joint video groups with different symbols. It's fine because you can combine them as well. But now, if you want to distribute one symbol to the other, then it's
Great. So thank you.
yeah,
This is work in progress.
Is that one of the other things?
yeah.
Yeah, go on.
You some I don't know whether it is really related, but I've heard that people working on the game to that they can encode expression logic and or more in models, and then run these symbolic institutions using their model checkers, which have already been matching theories. I was just wondering if you see any links with that.
So I don't, do you know about the matching?
No, yeah, you know,
Logical.
yes, they do have a matching logic, yeah, not. Yeah, but there's no work. Basically, the status of the work about the equational theories and matching is they do it almost in touch. Because they do it almost in touch. They do play with equation theories. And I haven't seen any work in because more they blend it on encoding of separation logic. I don't know. I can check.
Maybe we can take that
Yeah.
coffee break.
Yeah.
Wait, I can start a little bit more. So I do know that they do separation of things, okay. Just to say, Peter Maximovic, who's one of the original Gillian people, he's now working. And in particular,
That's why they found it.
I don't, no, I think it's difficult. But so I don't know what the innards are of matching, but we can go and find out because of it. But also just to say they were very interested in the debugger stuff. And we've been talking to them a bit about that. So there's one, and also the reason why I don't want to answer your question about is I was talking to Julian Bradfield. There seems to be stuff to do with the alternating floor and this stuff going on. I don't know what to say, but I want to say something.
You don't need it, don't do it, because it's only.
I think the point is to understand where the application goes. So we haven't fully understood all the applications of UX reasoning. We were only aiming at, well, what can pulse infer do? Let's do that one. And we knew how to do biodeduction and fix system errors, so we were doing that one. So we haven't mind what OX reasoning is doing. And now there's a huge plethora of products. Baking mentioned outcome logic to OHAPs, and you would know it. But basically variations on a theme of different triples. What does it need to be reachable? What does it need to be OX? Can you be OX and true? That's what outcome logic says, etc. So where in that space should we be? I don't at the moment see the limitation. I want to understand where can we do almost, where's our boundary? I don't know. So that's where I'm going at the moment. And then that's a little bit different from the combinations, but sort of more foundational before. So that's why I was finding it difficult to answer.
Okay, thank you very much.